Life cycle assessment is a technique to assess environmental impacts associated with all the stages of a product's life from cradle to grave. Designers use this process to help critique the products. LCAs can help avoid a narrow outlook on environmental concerns by compiling an inventory of relevant energy and material inputs and environmental releases, evaluating the potential impacts associated with identified inputs and releases, interpreting the results to help make a more informed decision. Goals and purpose. The goal of LCA is to compare the full range of environmental effects assignable to products and services by quantifying all inputs and outputs of material flows and assessing how these material flows affect the environment. This information is used to improve processes, support policy, and provide a sound basis for informed decisions. Life cycle assessment: a systematic set of procedures for compiling and examining the inputs and outputs of materials and energy and the associated environmental impacts directly attributable to the functioning of a product or service system throughout its life cycle. The term life cycle refers to the notion that a fair, holistic assessment requires the assessment of raw material production, manufacture, distribution, use and disposal, including all intervening transportation steps necessary or caused by the product's existence. There are two main types of LCA. Attributional LCAs seek to establish the burdens associated with the production and use of a product, or with a specific service or process, at a point in time. Consequential LCAs seek to identify the environmental consequences of a decision or a proposed change in a system under study, which means that market and economic implications of a decision may have to be taken into account. Social LCA is under development as a different approach to life cycle thinking intended to assess social implications or potential impacts. Social LCA should be considered as an approach that is complementary to environmental LCA. The procedures of life cycle assessment are part of the ISO 14000 Environmental Management Standards. In ISO 14040-2006 and 14044-2006. GHG product life cycle assessments can also comply with specifications such as PAR 2050 and the GHG Protocol Life Cycle Accounting and Reporting Standard. Four main phases. According to the ISO 14040 and 14044 standards, a life cycle assessment is carried out in four distinct phases as illustrated in the figure shown to the right. The phases are often interdependent in that the results of one phase will inform how other phases are completed. Goal and scope. An LCA starts with an explicit statement of the goal and scope of the study, which sets out the context of the study and explains how and to whom the results are to be communicated. This is a key step, and the ISO standards require that the goal and scope of an LCA be clearly defined and consistent with the intended application. The goal and scope document therefore includes technical details that guide subsequent work. The functional unit, which defines what precisely is being studied and quantifies the service delivered by the product system, providing a reference to which the inputs and outputs can be related. Further, the functional unit is an important basis that enables alternative goods or services to be compared and analyzed. So to explain this, a functional system which is inputs, processes and outputs contains a functional unit that fulfills a function. For example, paint is covering a wall, making a functional unit of 1 square meter covered for 10 years. The functional flow would be the items necessary for that function, so this would be a brush, tin of paint and the paint itself. The system boundaries. any assumptions and limitations. The allocation methods used to partition the environmental load of a process when several products or functions share the same process. Allocation is commonly dealt with in one of three ways: system expansion, substitution, and partition. Doing this is not easy, and different methods may give different results, and the impact categories chosen, for example, human toxicity, smog, global warming, eutrophication. Life cycle inventory. Life cycle inventory analysis involves creating an inventory of flows from and to nature for a product system. Inventory flows include inputs of water, energy, and raw materials, and releases to air, land, and water. To develop the inventory, a flow model of the technical system is constructed using data on inputs and outputs. The flow model is typically illustrated with a flow chart that includes the activities that are going to be assessed in the relevant supply chain, and gives a clear picture of the technical system boundaries. The input and output data needed for the construction of the model are collected for all activities within the system boundary, including from the supply chain. The data must be related to the functional unit defined in the goal and scope definition. Data can be presented in tables, and some interpretations can be made already at this stage. The results of the inventory is an LCI which provides information about all inputs and outputs in the form of elementary flow to and from the environment from all the unit processes involved in the study. Inventory flows can number in the hundreds depending on the system boundary. For product LCAs at either the generic or brand-specific level, that data is typically collected through survey questionnaires. At an industry level, care has to be taken to ensure that questionnaires are completed by a representative sample of producers, leaning toward neither the best nor the worst, and fully representing any regional differences due to energy use, material sourcing, or other factors. The questionnaires cover the full range of inputs and outputs, typically aiming to account for 99% of the mass of a product, 99% of the energy used in its production, and any environmentally sensitive flows, even if they fall within the 1% level of inputs. One area where data access is likely to be difficult is flows from the technosphere. The technosphere is more simply defined as the man-made world, considered by geologists as secondary resources. These resources are in theory 100% recyclable. However, in a practical sense, the primary goal is salvage. For an LCI, these technosphere products are those that have been produced by man, and unfortunately those completing a questionnaire about a process which uses man-made product as a means to an end will be unable to specify how much of a given input they use. Typically, they will not have access to data concerning inputs and outputs for previous production processes of the product. The entity undertaking the LCA must then turn to secondary sources if it does not already have the data from its own previous studies. National databases are data sets that come with LCA practitioner tools, or that can be readily accessed, are the usual sources for that information. Care must then be taken to ensure that the secondary data source properly reflects regional and national conditions. Life cycle impact assessment. Inventory analysis is followed by impact assessment. This phase of LCA is aimed at evaluating the significance of potential environmental impacts based on the LCI flow results. Classical life cycle impact assessment consists of the following mandatory elements: selection of impact categories, category indicators, and characterization models. The classification stage, where the inventory parameters are sorted and assigned to specific impact categories, and impact measurement, where the categorized LCI flows are characterized using one of many possible LCIA methodologies into common equivalence units that are then summed to provide an overall impact category total. In many LCAs, characterization concludes the LCIA analysis. This is also the last compulsory stage according to ISO 14044-2006. However, in addition to the above mandatory LCIA steps, other optional LCIA elements, normalization, grouping, and weighting, may be conducted depending on the goal and scope of the LCA study. In normalization, the results of the impact categories from the study are usually compared with the total impacts in the region of interest, the U.S. For example, grouping consists of sorting and possibly ranking the impact categories. During weighting, the different environmental impacts are weighted relative to each other so that they can then be summed to get a single number for the total environmental impact. ISO 14044-2006 generally advises against weighting, stating that weighting shall not be used in LCA studies intended to be used in comparative assertions intended to be disclosed to the public. This advice is often ignored, resulting in comparisons that can reflect a high degree of subjectivity as a result of weighting. Interpretation. Life cycle interpretation is a systematic technique to identify, quantify, check, and evaluate information from the results of the life cycle inventory and/or the life cycle impact assessment. The results from the inventory analysis and impact assessment are summarized during the interpretation phase. The outcome of the interpretation phase is a set of conclusions and recommendations for the study. According to ISO 14040-2006, the interpretation should include identification of significant issues based on the results of the LCI and LCIA phases of an LCA, evaluation of the study considering completeness, sensitivity and consistency checks, and conclusions, limitations and recommendations. A key purpose of performing life cycle interpretation is to determine the level of confidence in the final results and communicate them in a fair, complete, and accurate manner. Interpreting the results of an LCA is not as simple as 3 is better than 2, therefore alternative A is the best choice. Interpreting the results of an LCA starts with understanding the accuracy of the results and ensuring they meet the goal of the study. This is accomplished by identifying the data elements that contribute significantly to each impact category, evaluating the sensitivity of these significant data elements, assessing the completeness and consistency of the study, and drawing conclusions and recommendations based on a clear understanding of how the LCA was conducted and the results were developed. Referenced ed. More specifically, the best alternative is the one that the LCA shows to have the least cradle-to-grave environmental negative impact on land, sea, and air resources. LCA uses, based on a survey of LCA practitioners carried out in 2006. LCA is mostly used to support business strategy and R&D, as input to product-to-process design, in education and for labeling of product declarations. LCA will be continuously integrated into the built environment as tools such as the European ENSLIC Building Project Guidelines for Buildings or developed and implemented, which provide practitioners guidance on methods to implement LCI data into the planning and design process. Major corporations all over the world are either undertaking LCA in-house or commissioning studies, while governments support the development of national databases to support LCA. Of particular note is the growing use of LCA for ISO Type 3 labels called environmental product declarations, defined as quantified environmental data for a product with preset categories of parameters based on the ISO 14040 series of standards, but not excluding additional environmental information. These third-party certified LCA-based labels provide an increasingly important basis for assessing the relative environmental merits of competing products. Third-party certification plays a major role in today's industry. Independent certification can show a company's dedication to safer and environmental-friendlier products to customers and end users. LCA also has major roles in environmental impact assessment, integrated waste management and pollution studies. Data analysis. A life cycle analysis is only as valid as its data. Therefore, it is crucial that data used for the completion of a life cycle analysis are accurate and current. When comparing different life cycle analyses with one another, it is crucial that equivalent data are available for both products or processes in question. If one product has a much higher availability of data, it cannot be justly compared to another product which has less detailed data. There are two basic types of LCA data: unit process data and environmental input-output data, where the latter is based on national economic input-output data. Unit process data are derived from direct surveys of companies or plants producing the product of interest, carried out at a unit process level defined by the system boundaries for the study. Data validity is an ongoing concern for life cycle analysis. Due to globalization and the rapid pace of research and development, new materials and manufacturing methods are continually being introduced to the market. This makes it both very important and very difficult to use up-to-date information when performing an LCA. If an LCA's conclusions are to be valid, the data must be recent. However, the data gathering process takes time. If a product and its related processes have not undergone significant revisions since the last LCA data was collected, data validity is not a problem. However, consumer electronics such as cell phones can be redesigned as often as every 9 to 12 months, creating a need for ongoing data collection. The life cycle considered usually consists of a number of stages including materials extraction, processing and manufacturing, product use, and product disposal. If the most environmentally harmful of these stages can be determined, then impact on the environment can be efficiently reduced by focusing on making changes for the particular phase. For example, the most energy-intensive life phase of an airplane or car is during use due to fuel consumption. One of the most effective ways to increase fuel efficiency is to decrease vehicle weight, and thus, car and airplane manufacturers can decrease environmental impact in a significant way by replacing heavier materials with lighter ones such as aluminium or carbon fiber reinforced elements. The reduction during the use phase should be more than enough to balance additional raw material or manufacturing cost. Variants. Cradle to grave. Cradle to grave is the full life cycle assessment from resource extraction to use phase and disposal phase. For example, trees produce paper, which can be recycled into low-energy production cellulose insulation, then used as an energy-saving device in the ceiling of a home for 40 years, saving 2,000 times the fossil fuel energy used in its production. After 40 years, the cellulose fibers are replaced and the old fibers are disposed of, possibly incinerated. All inputs and outputs are considered for all the phases of the life cycle. Cradle to gate. Cradle to gate is an assessment of a partial product life cycle from resource extraction to the factory gate. The use phase and disposal phase of the product are omitted in this case. Cradle to gate assessments are sometimes the basis for environmental product declarations termed business-to-business EDPs. One of the significant uses of the cradle to gate approach compiles the life cycle inventory using cradle to gate. This allows the LCA to collect all of the impacts leading up to resources being purchased by the facility. They can then add the steps involved in the transport to plant and manufacture process to more easily produce their own cradle to gate values for The products, cradle-to-cradle or closed-loop production. Cradle-to-cradle is a specific kind of cradle-to-grave assessment, where the end-of-life disposal step for the product is a recycling process. It is a method used to minimize the environmental impact of products by employing sustainable production, operation, and disposal practices and aims to incorporate social responsibility into product development. For the recycling process originate new identical products or different products. Allocation of burden for products in open-loop production systems presents considerable challenges for LCA. Various methods, such as the avoided burden approach, have been proposed to deal with the issues involved. Gate-to-gate. Gate-to-gate is a partial LCA looking at only one value-added process in the entire production chain. Gate-to-gate modules may also later be linked in their appropriate production chain to form a complete cradle-to-gate evaluation. Well-to-wheel. Well-to-wheel is the specific LCA used for transport fuels and vehicles. The analysis is often broken down into stages entitled well-to-station or well-to-tank, and station-to-wheel or tank-to-wheel or plug-to-wheel. The first stage, which incorporates the feedstock of fuel production and processing and fuel delivery or energy transmission, and is called the upstream stage, while the stage that deals with vehicle operation itself is sometimes called the downstream stage. The well-to-wheel analysis is commonly used to assess total energy consumption, or the energy conversion efficiency and emissions impact of marine vessels, aircraft and motor vehicles, including the carbon footprint, and the fuels used in each of these transport modes. The well-to-wheel variant has a significant input on a model developed by the Argonne National Laboratory. The greenhouse gases, regulated emissions, and energy use in transportation model was developed to evaluate the impacts of new fuels and vehicle technologies. The model evaluates the impacts of fuel use using a well-to-wheel evaluation, while a traditional cradle-to-grave approach is used to determine the impacts from the vehicle itself. The model reports energy use, greenhouse gas emissions, and 6 additional pollutants: volatile organic compounds, carbon monoxide, nitrogen oxide, particulate matter with size smaller than 10 micrometers, particulate matter with size smaller than 2.5 micrometers, and sulfur oxides. Economic input-output life cycle assessment. Economic input-output LCA involves use of aggregate sector-level data on how much environmental impact can be attributed to each sector of the economy and how much each sector purchases from other sectors. Such analysis can account for long chains, which somewhat alleviates the scoping problem of process LCA. However, EIO LCA relies on sector-level averages that may or may not be representative of the specific subset of the sector relevant to a particular product, and therefore is not suitable for evaluating the environmental impacts of products. Additionally, the translation of economic quantities into environmental impacts is not validated. Ecologically based LCA. While a conventional LCA uses many of the same approaches and strategies as an eco-LCA, the latter considers a much broader range of ecological impacts. It was designed to provide a guide to wise management of human activities by understanding the direct and indirect impacts on ecological resources and surrounding ecosystems. Developed by Ohio State University Center for Resilience, Eco-LCA is a methodology that quantitatively takes into account regulating and supporting services during the life cycle of economic goods and products. In this approach, services are categorized in four main groups: supporting, regulating, provisioning and cultural services. Life cycle energy analysis. Life cycle energy analysis is an approach in which all energy inputs to a product are accounted for, not only direct energy inputs during manufacture, but also all energy inputs needed to produce components, materials and services needed for the manufacturing process. An earlier term for the approach was energy analysis. With LCA, the total life cycle energy input is established. Energy production. It is recognized that much energy is lost in the production of energy commodities themselves, such as nuclear energy, photovoltaic electricity, high-quality petroleum products. Net energy content is the energy content of the product minus energy input used during extraction and conversion, directly or indirectly. A controversial early result of LCEA claimed that manufacturing solar cells requires more energy than can be recovered in using the solar cell. The result was refuted. Another new concept that flows from life cycle assessments is energy cannibalism. Energy cannibalism refers to an effect where rapid growth of an entire energy-intensive industry creates a need for energy that uses the energy of existing power plants. Thus, during rapid growth, the industry as a whole produces no energy because new energy is used to fuel the embodied energy of future power plants. Work has been undertaken in the UK to determine the life cycle energy impacts of a number of renewable technologies. Energy recovery. If materials are incinerated during the disposal process, the energy released during burning can be harnessed and used for electricity production. This provides a low-impact energy source, especially when compared with coal and natural gas, while incineration produces more greenhouse gas emissions than landfilling. The waste plants are well fitted with filters to minimize this negative impact. A recent study comparing energy consumption and greenhouse gas emissions from landfilling against incineration found incineration to be superior, in all cases except for when landfill gas is recovered for electricity production. Criticism. A criticism of LCEA is that it attempts to eliminate monetary cost analysis, that is, replace the currency by which economic decisions are made with an energy currency. It has also been argued that energy efficiency is only one consideration in deciding which alternative process to employ, and that it should not be elevated to the only criterion for determining environmental acceptability. For example, simple energy analysis does not take into account the renewability of energy flows of the toxicity of waste products. However, the life cycle assessment does help companies become more familiar with environmental properties and improve their environmental system. Incorporating dynamic LCAs of renewable energy technologies may help mitigate this criticism. In recent years, the literature on life cycle assessment of energy technology has begun to reflect the interactions between the current electrical grid and future energy technology. Some papers have focused on energy life cycle, while others have focused on carbon dioxide and other greenhouse gases. The essential critique given by these sources is that when considering energy technology, the growing nature of the power grid must be taken into consideration. If this is not done, a given class of energy technology may emit more CO2 over its lifetime than it mitigates. A problem the energy analysis method cannot resolve is that different energy forms have different quality and value even in natural sciences, as a consequence of the two main laws of thermodynamics. A thermodynamic measure of the quality of energy is exergy. According to the first law of thermodynamics, all energy inputs should be accounted with equal weight, whereas by the second law diverse energy forms should be accounted by different values. The conflict is resolved in one of these ways. The value difference between energy inputs is ignored. A value ratio is arbitrarily assigned. The analysis is supplemented by economic cost analysis. Exergy instead of energy can be the metric used for the life cycle analysis.